Okay, here's the virtual office hour for Unit 1, Module 4. Contains all the questions that were covered in the office hours on Tuesday, Wednesday, Thursday, and Friday. So we went over the activity that we had in class. Okay, so all of these statements will be analyzed. So this nuclei with the same number of protons and different number of neutrons are isotopes, and that's our definition of an isotope. So when we looked at neon here, all of the neon nuclei that are shown here have the same number of protons, which is 10. They just differ by the number of neutrons, which is the top number is the sum of number of protons and neutrons. It's absolutely true. Nuclei with different numbers of protons are different elements. That's true if there are 7 protons, that is the element nitrogen. If there's 8 protons, that's the element oxygen. And if there are 9 protons, it's the element fluorine. So Z, or the number of protons, is definitive for the identity of the element. All the mass is inside the nucleus. That's true. Protons and neutrons are very massive compared to electrons. All the mass is inside the nucleus. And removal of an electron will change an atom to an ion, but will not change its identity. That's true. So if we write all of these different carbon 12s here with different charges, they all have 6 protons, but they have different number of electrons. The one that has the same number of protons and electrons is neutral and is the atom or atomic form. If there's a plus charge, then there are less electrons than protons, and if it's a negative charge, then they have more electrons than protons. So let's explore that some more in a table. So here we have different isotopes and or ions. And what we want to do is we want to determine the number of protons, number of neutrons, and number of electrons for each species. All right, so what we're going to do is we're going to fill in the Z value. So this is the number of protons each element has. We know that because if we look up the symbol on the periodic table, this is the integer associated with this element. So that means there are 8 protons for oxygen, 92 protons for uranium, 26 protons for iron, 82 protons for lead, 26 protons for iron again, and then 7 protons for nitrogen. Get this from the periodic table. All right, so it would look like this for uranium. So uranium would have the integer 72, which corresponds to 72 protons, but the mass 238, those are going to be the sum of the protons and the number of neutrons. All right, so let's see how this will work. So 17 oxygen has 17 protons and neutrons together inside the nucleus. But we know how many protons we have because we know it's oxygen. So 17 minus 8 would be the number of neutrons. For uranium, it'd be 238, which is the sum of protons and neutrons. Subtract it from the number of protons, and we would get neutrons there. Iron, the same. 56 minus 26. For lead, the same. So we subtract the two numbers. The top minus the one below to get the number of neutrons. That is because, so for any symbol, we would see that the top or the superscript is the sum of number of protons and number of neutrons. Z is the number of protons and X is the identity. So if we want to know the number of neutrons, then we just subtract A from Z. Okay, so in this case, 17 oxygen would give us 9 neutrons. Here we'd have 146 neutrons in uranium-238. 30 neutrons for 56 iron. 126 neutrons for 208 lead. 28 neutrons for 54 iron. And 8 neutrons for 15 nitrogen. Okay, so when we determine the number of electrons, we have to take into account the charge. If the charge is neutral, meaning there's no pluses or minuses, then we know we have the same number of electrons as protons because they exactly cancel out. So we have 8 protons in oxygen, we have 8 electrons. We have 92 protons in uranium and it's neutral, we get 92 electrons. Same with iron, 26 protons, 26 electrons. Okay, now if we have a total charge, now we have to be careful. Right, so the total charge for oxygen was 8 minus 8. Plus 8 for 8 protons, minus 8 for 8 electrons. Same here, 92 minus 92, that was 0. And 26 minus 26. But now when lead is plus 2, now we're going to see we have 82 protons. That never changes for lead. But we're going to have 80 electrons to give a total charge of plus 2. So we need 80 electrons. For iron with a plus 3, we have 26 protons. And so we have 23 electrons. 23 electrons subtracting from 26 gives us plus 3. For minus 3, nitrogen, we have 7 protons, and here we would have 10 electrons. That minus 10 from the 10 electrons plus 7 gives us a minus 3. So these are all of the types of calculations of this way that you would be expected to be able to do. Okay, so let's look at some features of the mass spectrum and calculating some molecular formulas or determining some molecular formulas. We were given this problem, so keep in mind we removed the y-axis, we put in the I don't care axis, we don't use any information of the y-axis for the mass spectrum. All of our attention is on the x-axis. The x-axis is here because the maximum mass on the x-axis is the molecular mass. So that's really important for us. So for here it's 205. So the molecular mass for this problem is 205. Right, now we have some elemental composition for carbon, fluorine, and chlorine. And we're asked to determine the empirical and molecular formula. We've shown 2 ways to do this in class. So we will first do method 1 and then method 2. Method 1 assumes a 100 gram sample. Why? Because that means immediately the percents can be turned into grams and we can convert the mole ratios. So we put 11.8 grams of carbon, 18.6 grams of fluorine, and 69.6 grams of chlorine. And we calculate that, we get 0.98 moles of carbon, 0.98 moles of fluorine, and 2 moles of chlorine. So we have these ratios in every 100 gram sample, and now we want to normalize it to the lowest moles. We want to get integers. So we divide by the lowest number of moles here. That's what we do. And we see that at the empirical formula level, the empirical formula is going to be 1 carbon for every fluorine for every 2 chlorine. That's what the mole ratios give us when we divide by the lowest number. Now we need to ask ourselves, what is the mass of this empirical formula? If it's the same as the molecular mass, we're finished. So let's see what happens. When we add up the molecular mass, here we see that it weighs, the mass is 101 grams. But our molecular mass is 200. So that means we have to take all of our coefficients and multiply by 2 to get the 205 grams per mole molecular mass. All right, so let's look at method 2. So method 2 starts with the molecular mass from the mass spectrum, 205, and now we take each of the percents that are given and find out how many grams are in, how many grams of carbon and how many grams of fluorine do we have in this 205. So if we do that, take 205 and multiply by these percents, we see to get the grams of chlorine, we take 205 times 0.118, which is 11%, almost 12%. And we see there's 24 grams of carbon in the sample. For fluorine, it's 38 grams of fluorine and 70 grams of chlorine. So that's how many grams are in 1 mole of this substance. We divide by the atomic masses here, 12 for carbon, 38 for fluorine, 70 for chlorine. And we see that in every particle of this substance, we're going to have 2 carbon atoms, 2 fluorine atoms, and 4 chlorine atoms, giving us a molecular formula of C2F2Cl4. Now method 2 gives us the molecular mass first. If we can factor a number out of each of the coefficients, then we would have an empirical formula. We see we can do that. If we factor a 2 out, that would give us the empirical formula CFCl2. And that's the empirical formula. And that would be the answer for this problem. All right, so let's do this a couple more times. You want some practice? Definitely suggest that you try to do problems like this and then compare your answers. Here we have 100 grams. How many grams of carbon are in 100 grams of C6H12O6? So we did this in class. We found out that to get the molecular mass, what we're doing is we're taking 6 carbons times 12, it's 72 grams of carbon, 12 atoms of hydrogen times 1 gram per mole gives us 12 grams of hydrogen, and 6 times 16, 96 grams of oxygen in each mole of sample, giving us a total of 180 grams per mole. So there's 2 ways to do this. We could recognize that 100 grams is about half a mole, and so if 72 grams of carbon are in 1 mole, then 40 grams of carbon are in half a mole. But the formal way to do this problem is to say that if we have 100 grams of C6H12O6, then the first thing we'll do is we'll convert to moles of C6H12O6, and then convert using that information. We'll get moles of carbon, because there's 6 moles of carbon for every 1 mole of C6H12O6. And then for every 1 mole of carbon, we get 12 grams. If you do this calculation, you get 40. So we have grams of C6H12 going to moles of C6H12O6, going to moles of carbon to grams of carbon. So with that story, any calculation can really unfold that way, as long as you can put in words how the calculation will be done. Again, 2 different ways to do this problem. Okay, so these are the 2 additional problems that were done in office hours. So if you want to practice and compare your answer with us, you can. I do both methods as a way for you to check your answers. All right, so I'm just going to step through this fairly quickly. So method 1, we assume 100 grams. And that gives us instantly the grams of each of the sample, which we then have to convert to moles, which we're going to do now. And this gives us what will be our molar ratio, because we're going to have, right, in any sample, there's going to be this kind of molar ratio inside the molecule. So when we divide by the lowest number here, we get the molar ratios of the empirical formula, which would be C1, Cl1, F2. The empirical mass of this substance is going to be 85.5 grams per mole. And then we ask ourselves, is this the molecular mass? And when we look at the circle, the answer is no, it is not 85.5, but it looks like twice that, 170. So if it is 170, then we have to divide by 85.5, and we see we need 2 empirical units per molecule to get the entire molecule mass. So if we take 2 and multiply it by each of the coefficients, we get C2, Cl2, F4. Okay, so now let's look at method 2. So method 2 looks at the percentages of each atom's mass into the molecular mass. So at 172 grams times 0.1403, that gives us the grams of carbon, 24 grams. We do the same thing with chlorine, and that gives us the grams of chlorine. And if we do 172 times 0.44, we get the amount of grams of fluorine. So we take and divide by the atomic mass each number, we get the molecular ratio. The molecular ratios here, number of atoms, C2, Cl2, F4, which is what our other answer gave us. So that's the molecular formula. We have to factor out a common multiple here, which is 2. And so to get the empirical formula, so our empirical formula would be CClF2. Okay, so please keep in mind you can use either method. Both give you the same answer. The main thing is to feel confident with either method. Practice it with as many problems as you can. All right, so the last example worked in class looked like this. So here we have another mass spectrum and percents. So in method 1, 100 gram sample. That allows us to convert to moles of carbon. And then we do the same thing for hydrogen. Get moles of hydrogen. Same thing for nitrogen. Moles of nitrogen. All right, so now we're going to divide by the lowest number of moles, which gives us integers. So now our empirical formula is constructed with this data. 4.5 divided by 2.2 is 2. 13.7 divided by 2.2 is 6. 2.2 divided by 2.2 is 1. So that gives us the empirical formula C2H6N. We now add up the empirical mass to see if it's the same as the molecular mass. So we see it's 44 grams per mole. But our molecular mass is not 44 grams per mole, it's 88 grams per mole. So that means that we have to multiply our empirical unit by 2, giving us C4H12N2. Would be our molecular formula. We could have also done this with method 2, so we'll do that quickly. So here's method 2, 88 grams per mole times 0.545 gives us the grams of carbon. 88 grams per mole times 0.137 gives us the grams of hydrogen. And 88 grams per mole times 0.318 would give us the moles of nitrogen. When we do this calculation, we see we get 48 grams. So out of the 88, 48 grams is carbon. Divided by 12 gives us 4. 88 grams times 0.137 is 12 grams of hydrogen. Divided by 1 gram per mole gives us 12. And 28 grams of nitrogen divided by 14 gives us 2. So from the method 2, we directly get the molecular formula, which is going to be C4H12N2. If we can factor out a common multiple, we can determine the empirical formula. There is one. All the numbers are divisible by 2. If we do that, we get C2H6N. That is our empirical formula, same as method 1. All right, well, so these were all the questions that were presented and worked through in office hours. And keep in mind, we will start Unit 2, Module 1 starting next week.